All right, so we're going to wrap up section 11.6. We'll cover one more topic in the section and do an example that corresponds to this topic. So, given a plane with normal vector n and any point P1 not on the plane, the distance capital D between the plane and P1 is capital D equals the absolute value of n dotted with the vector P naught to P1 divided by the magnitude of n, where P naught is any point on the plane. All right, so we'll do one example of this. So we'll look at page 747, number 14, which says find the distance d between the points 2, 0, negative 4 and the plane x plus 2y plus 4z minus 3 equals 0. All right, find the distance between, so they give us a point. This is the point that's not on the plane, so we're going to call it P1, which is 2, 0, negative 4. And the plane x plus 2y plus 4z minus 3 equals 0. All right, so we want to use this formula above. So we need a normal vector, we need a point that's not on the plane, we need a point that is on the plane. So they give us a point not on the plane, and they just give us this. Now remember, we know how to quickly see what the normal vector is using the coefficients of x, y, and z. So our normal vector, we can see, is 1, 2, 4. All right, same thing I talked about with lines. We can use, if this vector is perpendicular to this plane, then any non-zero multiple of this is perpendicular to the plane. So you can multiply this by -1, you can multiply it by 10, and that's a perfectly legitimate normal vector as well. And your answer is still going to come out the exact same, regardless of which normal vector. It's not going to change your distance, and regardless of what point you use that's on the plane, because right now we still need a point on the plane, which we don't have. So this equation governs every single point on the plane. So every point on the plane satisfies this equation. So if you need to find a point on the plane, you do just like you would with the equation that only has two variables in it. You normally have an independent variable. You have an independent variable and a dependent variable. You plug in whatever number you want to, it spits out the other number, and now you have a point. Here, you plug in whatever two numbers you want to, and it'll spit out the other number, and now you have an x, y, and a z. So you could say, okay, well, I mean, the easy thing is plug in zeros. So you say, okay, well, I want to plug in x is 0, y is 0, whatever you want to do. Because x has a coefficient of 1, I'm going to plug in y equals 0 and z equals 0, and that's going to give me what x is, and then I'll have a point. So to find the point on the plane, plug in for instance, because you don't have to plug in 0. I mean, 0 is oftentimes the easiest things to plug in. For instance, what did I say? Y equals 0 and z equals 0. So if I plug in y equals 0 and z equals 0, then I get x minus 3 equals 0. So that gives me x equals 3. And now I have a point 0, 0, 3. So now my P naught, my point on the plane, P naught is, 3, 0, 0. 3, 0, 0. So now using that, I can go and I can use this formula. So our normal vector we already have. Let's find the vector P naught to P1. So our P1, so we're going to do 2 minus 3, which gives us -1, 0 minus 0, which gives us 0, and then -4 minus 0, which gives us -4. And then I need to do n dotted with this vector. So n dotted with P naught to P1 is going to give us 1 times -1, which gives us -1, 2 times 0, which gives us 0, and then 4 times the -4 gives us -16. So we get -17, and we have to take the absolute value of this. So gives us 17 there. And the only thing left to do is find the magnitude of n, and then do the quotient of these, this and that magnitude. So the magnitude of n is equal to the square root of 1 plus 4 plus 16. So the square root of 21. And that gives us our d. Our d is 17 over the square root of 21. All right, so we'll stop 11.6 there, and then we'll start chapter 12, section 12.1 in our next video.